we will see one of the iterative method which has been studied in numerical analysis topics. So that is Rayleigh's power method. So basically Rayleigh's power method is the numerical technique which is used to estimate either the largest or the smallest eigenvalue and the corresponding eigenvector of a square matrix. So Rayleigh's power method is iterative method. Iterative technique means we have to follow the same procedure again and again, used to estimate largest or smallest eigenvalue and its corresponding eigenvector. The question is when we have to apply the power method. So if suppose A is a real square matrix of order n, such that A has n real distinct eigenvalues. So since the matrix has n distinct eigenvalues and hence it has n linearly independent eigenvectors. Rayleigh's power method can be used for a real square matrix only when it has real distinct eigenvalues. So if it has real distinct eigenvalues, then the corresponding eigenvectors are linearly independent. The condition should be noted. It has, for a square matrix of order n real distinct eigenvalues should be there. So if suppose A is a real square matrix of order n, then the eigenvalues can be ordered in magnitude as lambda 1 greater than lambda 2 modulus of lambda 2 modulus of lambda 3 and so on modulus of lambda n. What we have to remember is that Rayleigh's power method is one of the iterative method which is used either to find the largest or the smallest eigenvalue and hence the corresponding eigenvector. And when to apply? It has to be applied on a square matrix, real square matrix, only when it has n linearly independent eigenvalues and hence n linearly independent eigenvectors. What is eigenvector? A non-zero vector x is called eigenvector if there exists a number, if there exists lambda, such that Ax is equal to lambda x. Here lambda is called eigenvalue and x is the corresponding eigenvector. Now what is the procedure for Rayleigh's power method? We will see how to carry out the Rayleigh's power method. So procedure is, we will be having a square matrix A of order n. This is a real square matrix of order n. So in order to carry out the Rayleigh's power method, we have to have an initial guess for eigenvector. So x is eigenvector. We will take one of initial guess. So that is x is equal to 1 1 1 all 1 eigenvector which is of order n by 1. This is the initial approximation for eigenvector. We can take x as 1 all zeros or 0 1 all zeros. Likewise we may have different initial approximations for x. So most used the initial approximation is all ones vector. Now we take the product A into x. So A is n by n matrix and x is n by 1 vector. Then we will have a one vector which is of order n by 1. So we get a one vector of order n by 1. From this we have to take maximum entry out. So if you want to find the largest eigenvalue, so here we will find the largest eigenvalue. The procedure is for largest eigenvalue, because we have different procedure for smallest eigenvalue. So we have to take maximum entry out from the product A into X. So if I take the maximum entry out, I can write it as Ax is equal to lambda into. So after taking some quantity out, X is changed to X dash. Now after the first iteration, we have lambda is eigenvalue and X dash is the corresponding eigenvector. So this is first iteration. So now to carry out the second iteration, our approximation for eigenvector is X dash. So for second iteration, X dash is eigenvector. Now again we have to find the product Ax dash. So this is also n by 1 vector. Again we have to take the maximum entry out. So therefore we have Ax dash is equal to lambda dash X double dash. So after second iteration, lambda dash is eigenvalue and X dash double dash is the corresponding eigenvector. So likewise, so if you want to carry out the third iteration, then our initial approximation for eigenvector is X double dash, and again we have to find X double dash. From this also take a maximum entry out. So we can write it as X double dash is equal to lambda double dash X triple dash. So after third iteration, this is eigenvalue and this is a corresponding eigenvector. So we have to carry out the procedure until if suppose there are number of iterations are specified, until that iterations we have to carry out. Otherwise, if suppose the consecutive eigenvalues are almost near, suppose if I want to stop at this step, either they have to mention find the largest eigenvalue of the square matrix, which has to be performed up to 3 iterations, means we have to stop. If they are not given any iterations, then we have to compare the consecutive eigenvalues. If they are almost same, then we have to stop. If suppose lambda double dash minus lambda dash is almost equal to 0, or sometimes they mention find the find the largest eigenvalue of the square matrix, which has to be connected up to 2 decimals. Means suppose lambda dash is equal to some 2.0582 and lambda double dash is equal to 2.059396. Then if suppose they ask to find lambda such that they are connected to 2 decimals, so these two are connected to 2 decimals, therefore we can stop at this step. So this is how the Rayleigh's power method is used to find the largest eigenvalue. This what the procedure we have seen so far is for largest eigenvalue. So how to think about smallest eigenvalue? For smallest eigenvalue, what we will do is, if suppose A is a matrix and lambda is the eigenvalue which is largest, then for A inverse 1 by lambda is the smallest. So for it's provided lambda is non-zero. So here if you want to find we have to find smallest A value for A, then first you have to find A inverse, and afterwards largest eigenvalue of A inverse will be smallest eigenvalue for A, because if suppose lambda is eigenvalue of A inverse, then 1 by lambda is eigenvalue of A. If suppose this is largest, then 1 by lambda will be smallest. This is how the same method can be applied to find the smallest eigenvalue as largest eigenvalue. Originally the procedure is applied mainly for finding the largest eigenvalue of the real square matrix of order n, which has n real distinct eigenvalues and hence n linearly independent eigenvectors.